So in this part, we are going to cover three important techniques used in designing and analyzing algorithms. Number one is dynamic programming. It is dynamic programming. Number two is greedy programming. Number two is greedy programming. Number three, it is amortized analysis. Amortized analysis. Okay, so we'll start with the dynamic programming. In the earlier parts, we have presented other widely applicable techniques, like we have done divide and conquer, we have done randomization, we have done how to solve recurrence relations, we have done simple techniques for searching and sorting. Now the techniques in this part are somewhat more sophisticated, but they help us to attack many computational problems. So dynamic programming typically applies to optimization problem in which we make a set of choices in order to arrive at an optimal solution. So as we make choices, sub-problems of the same form often arises, and the dynamic programming is effective when a given sub-problem may arise from more than one partial set of choices. Consider a very simple example or a very simple recursive program to find a Fibonacci of a number. If you are writing a program to find a Fibonacci of a number, you can write something like this: Fibo of n is if n is equal to 0, then we are going to return 0, else if n is equal to 1, then we are going to return 1, else return Fibo of n minus 1 plus Fibo of n minus 2. Now this is a very simple recursive program to find the Fibonacci of a number. So what is a Fibonacci of a number? I think some of you may be confusing what is the Fibonacci of a number. Let us find out Fibonacci of some simple numbers. This is how I am going to represent the Fibonacci. Assume this is the number n and this is the Fibonacci of n. If Fibonacci of 0 is 0, Fibonacci of 1 is 1. It is already defined. Fibonacci of 2 is 0 plus 1, that is a sum of last two terms, which is 1. Fibonacci of 3 is 1 plus 1, which is 2. Fibonacci of 4 is 1 plus 2, which is 3. Fibonacci of 5 is 2 plus 3, which is 5. Fibonacci of 6 is 8. Fibonacci of 7 is 13. So mathematically, if I say Fibonacci of a number, n, then Fibonacci of a number n can be defined as 0 if n is equal to 0, it is 1 if n is equal to 1, or it is Fibonacci of n minus 1 plus Fibonacci of n minus 2 otherwise. This is how you can find the Fibonacci of a number. So I programmed the same thing into this program which I designed here, and now I'll try to see how you can use this program to find the Fibonacci of a number. Okay, so see, this program is a recursive program, so obviously you are going to do so many recursive calls here, and I'm going to list down some of those recursive calls to find the Fibonacci of simple numbers. Okay, so let me draw a line here. This is the program. So let us suppose we want to find the Fibonacci of a number which is 5. So if I write Fibonacci of a number which is 5. So here in this above program, the value of n is 5 and 5 is not equal to 0. The line number 1, it failed. Fibonacci 5 is not equal to 1. So we are going to execute the line number 3. So it is going to call Fibonacci of 4 plus Fibonacci of 3. Now to find the Fibonacci of 4, we have to find Fibonacci of 3 plus Fibonacci of 2. To find Fibonacci of 3, we have to find Fibonacci of 2 plus Fibonacci of 0. To find Fibonacci of 2, we have to find, so this is Fibonacci of 1. This is Fibonacci of 1. Fibonacci of 2 is Fibonacci of 1 plus Fibonacci of 0. Okay. In the same way, if you find the Fibonacci of this number 2, then this is Fibonacci of 1 plus Fibonacci of 0. And this is Fibonacci of 3. So Fibonacci of 3 can be found out like this. It is Fibonacci of 2 plus Fibonacci of 1. And Fibonacci of 2 is Fibonacci of 1 plus Fibonacci of 0. Fibonacci of 0. So this is how you can find the Fibonacci of a number which is 5. And you already know the values which from this program. Here Fibonacci of 1 is 1. Fibonacci of 0 is 0. So if we do 1 plus 0, we are going to get 1. That is Fibonacci of 2 is 1. Here Fibonacci of 1 is 1. And 1 plus 1 is 2. So Fibonacci of 3 is going to give us 2. In the same way, Fibonacci of 1 is 1. Fibonacci of 0 is 0. Fibonacci of 1 is 1. Fibonacci of 0 is 0. Now Fibonacci of 2 is 1. 1 plus 0 is 1. Fibonacci of 2 is 1. And Fibonacci of 4 is 2 plus 1, which is 3. Fibonacci of 3 is 1 plus 1, which is 2. And Fibonacci of 5 is 5. 3 plus 2 is 5, which you can verify from this above table. Now from this Fibonacci of a number, you can find out how many times we have done these recursive calls. How many times we have done these recursive calls. Let me list this out. Okay, so the recursive calls which we have done is Fibonacci of 0. If you can see this, we called Fibonacci of 0. This is Fibonacci of 0. 1, 2, 3. Right, so if we called Fibonacci of 0, then we called it 3 times. How many times we called Fibonacci of 1? It is Fibonacci of 1. If we discuss about Fibonacci of 1, then it is 1, 2, 3, and 4, and 5. We called it 5 times. We called Fibonacci of 1 5 times. Okay. How many times we called Fibonacci of 2? If you discuss about Fibonacci of 2, then it is 1, 2, and 3. We called Fibonacci of 2 3 times. Then how many times you called Fibonacci of 3? It is 1 and 2. Fibonacci of 3 we called 2 times. So Fibonacci of 3 we called 2 times. And how many called we called Fibonacci of 4? Fibonacci of 4 is called 1 time, and Fibonacci of 5 is also called 1 time. That is the initial recursive calls. So if you can see, whenever we are going to make these recursive calls, we are going to waste a lot of computational power. Generally in recursive programming, it happens that when you do recursive calls, there will be so many overlapping subproblems which repeat itself. When I'm saying the term which is called as overlapping subproblem. Overlapping subproblems. Overlapping subproblems. Overlapping subproblem means these are the kind of problems which repeat themselves, which overlap with each other. For example, here you can see Fibonacci of 0 we already calculated once, but because of these recursive calls, we are going to call it 3 times, and every time we are going to call Fibonacci of 0, we have to calculate it. The system has to do some processing. In the same way, when we called Fibonacci of 1, then you can see Fibonacci of 1 we called 5 times in this recursive calls, and every time we found the value of Fibonacci of 1, every time we are calling it again, and we are trying to find the values. right? So all these recursive calls are stored in stack, and every time we have to perform the computation. So when we so in the case of dynamic programming principles, we say that all the recursive calls, why are you calculating them again and again? Why are you wasting so much time and space and resources just to calculate again and again? Every time when you evaluate that number, whenever you evaluate, for example, Fibonacci of 0, store it in an array, and next time when you have to make that recursive call, don't make it, just take that value from that array. In the same way, here in this case, we are calculating Fibonacci of 1 5 times. So instead of calculating it 5 times, store the value of Fibonacci of 1 into an array, and next time whenever you have to find or call the value of Fibonacci of 1, access that value from the array, because you don't have to call it again and again, right? So here in this case, if you see Fibonacci of 5 is a very small number, but if you take a very large number or bigger number, then this condition become more severe, because you have to make so many recursive calls. For a value of n tending to 1000, we have to call millions of recursive calls which are repeating itself. So better way is, instead of wasting so much time again and again to call these values, calculate these values in stack, in form, just store them, and next time use it. Once you already stored, use it. So how we can apply the principles of dynamic programming into the same function is, we are going to store these values. We already know what is the value of Fibonacci of 0, and we already know what is the value of Fibonacci of 1. So we can modify the same program in such a manner so that we don't have to waste so much time and don't have to waste so much space. So let me write that improved program here. So again, we want to find Fibonacci of a number which is n. So for that purposes, first of all, declare an array with n index locations. So assume we have an array. A with n index locations. Assume we have an array A with n index locations, where index locations are starting from 0 to 1 and so on. Okay. So at index location 0, we are going to store 0. At index location 1, we are going to store 1. Okay, so that we don't have to calculate it again and again. So this is the array which we have. This is the array A. Index locations are 0, 1, 2, 3, 4, 5, 6. So at index location 0, we are going to store 0. At index location 1, we are going to store 1. And for other locations, for example, if you want to find Fibonacci of n, then we have to calculate those values, and we have to store those values so that we don't have to calculate them again and again, like in this given array, like in this array. We don't want to calculate it again and again. So we can do something like this. For I is equal to 2, I less than or equal to n, I plus plus, because if you want to find the Fibonacci of n, then we need that index location. And see, and when I'm saying assuming we have an array of a of n, just assume that we created that array from index location 0 to n. Last index location is n, just for simplicity. So if you want to find the Fibonacci of a number which is I, then it is a of I minus 1 plus a of I minus 2. That means if the value of I is 2, if the value of I from this statement, if the value of I is 2, so this statement is a of 2 is equal to a of 1 plus a of 0, which we already calculated. We already stored the value of a of 1 and a of 0. Now we are going to use that value till we want to find the number n. And after that, you can just return the value of a of n, and this will again find the Fibonacci of that number. So this is a non-recursive program where instead of calling these again and again, we just store their values so that we can use it at a later point of time. In the same way, if you look at this array, if the value of I is 2, when the value of I is 2, so we are going to do 0 plus 1. 0 plus 1 is 1. When the value of I becomes 3, and 3 is less than n. So we are going to call a of 3 is equal to a of 2 plus a of 1. Right, so a of 2 plus a of 1. So this value stored at index location 2 is 1 and value stored at index location 1 is 1. So 1 plus 1 is 2. In the same way, we are going to find the value of a of 4. So a of 4 is a of 2 plus a of 3, which is 1 plus 2, which is 3. Now it is 5, it is 8, and so on. So you can find the values of Fibonacci of a number in such fashion, in such manner. And I believe this is one of the easiest method which we can do. But still we can improve this method. Instead of using an array, we can still minimize the array size to find the Fibonacci of a number, but that is not a point. You can easily write a program to find the Fibonacci of a number which is not even using an array, because if you are using this kind of array, then this kind of array is going to use order of n space to find the Fibonacci of a number. Order of n space. Okay, so we can still minimize it to find the Fibonacci number. We can find it in order of 1 time, order of n 1 space, and order of n time, order of n time. So right now here the main purpose is I want to minimize these many recursive calls, because if you can minimize these many recursive calls, we can save a lot of time and we can save a lot of space. This is the basic principle behind the concept of dynamic programming. So it's dynamic programming is like divide and conquer method, which solves the problem by combining the solutions to sub problems. Right, so here sub problems like this Fibonacci of 1, Fibonacci of 2, these are the sub problems which we calculated again and again. And here we are going to use divide and for example, we used some problems where we have sub problems which are recursively calling itself. Then we are going to combine their solution to solve the original problems. So generally you can say that we apply dynamic programming when the sub problems are overlapping. That means they are repeating again and again. That is when some problems share the sub problems. So dynamic programming solves each sub problem just once and then saves it answers in a table, and thereby avoiding the work of recomputing the answers every time it solves each sub problem. So we generally apply the dynamic programming to optimization problem. Such problems can have many possible solutions, and each solution has a value, and we wish to find that value with the optimal or minimal or maximum value. So we can call such solutions as optimal solution to this problem. So as opposed to the optimal solution, since there may be several solutions that can achieve the optimal value. So generally, if you do dynamic programming, if you generally follow the principles of dynamic programming, then we are developing a dynamic programming algorithm with a 4 sequence of steps. Number 1, every time we are going to characterize the structure of an optimal solution. The structure of an optimal solution. Structure of an optimal solution. Second thing which we need to do is recursively define the value of the optimal solution. Recursively define the value of an optimal solution. And the third step, which is important here, is compute the value of optimal solution, where typically we do it in bottom-up fashion. So we compute the value of an optimal solution typically in bottom-up fashion. Okay. And the step 4 is construct an optimal solution for computed information. Construct an optimal solution for computed information. Construct an optimal solution for computed information. For example, if you consider this previous case, in this case, if you see this recursive tree, in this complete recursive tree, let me line it like this. This is the recursive tree which we are discussing. So in this complete recursive tree, if you go from bottom to up, that means from here to here, this is bottom and this is bottom to up. So if you go from bottom to up and you check this array, check the program which we written here. Now in this program we are calculating the values from bottom to up. That means initially we know the value of Fibonacci of 0, we know the value of Fibonacci of 1. Now we are filling this array, from bottom to up, and we are storing those values. And if you check the complete steps I have taken, the first step I have taken is I'm characterizing the structure of an optimal solution. So this was the characterization. This was the characterization where I'm characterizing the structure of the optimal solution. Then I'm going to recursively define the value of optimal solution. So these are the recursively defining the values of optimal solution, and we are computing those values, and we are computing here in this array, we are computing those values in a bottom up fashion, and then we construct an optimal solution on the computed information. Okay, and here the steps 1, 2 and 3, these 3 steps, if you discuss about these 3 steps, step 1, 2 and 3, these 3 steps form the basis of a dynamic programming solution to a problem. And if we need only the value of an optimal solution and not the solution itself, then we omit the step 4. So when we do perform the step 4, we sometimes maintain additional information during the step 3 so that we can easily construct an optimal solution. So the first type of problem which we are going to discuss with dynamic programming is matrix chain multiplication problem. We are going to discuss so many different problems here, approximately 5 to 6 different dynamic programming problems we are going to discuss. The first problem will be the matrix chain multiplication. Now, after doing the matrix chain multiplication, we are also going to discuss the longest common subsequence problem, and we are going to discuss other problems also that we will see in a later point of time. So initially we'll start with the matrix chain multiplication problem, and I'll tell you what is that problem. I'm going to define the structure of that problem. I'm going to define a recursive relation to solve that problem, and then we are going to change that problem to a dynamic programming problem.